What's going on, everybody? This is Mr. Diamond, and we're going to be working out the relative velocity example problem here. Now, I have usually worked out these examples ahead of time, but I do not have the time to do that this time, so this might be an absolute mess, and I may have to back up. And if I do that, I guess I may end up deleting this video, and you may not hear this part at all. But hopefully I don't do that, and hopefully we can just kind of make it through here together. I do have... Although it looks like I lost it for a second. Let me go and track it down. I am going to need, or we will both need, our Chapter 1 formulas for this example problem. So do make sure that you've got your Chapter 1 formulas close by so we can use them for this if we need it, which we will, hint, hint. But we're going to start this just like we do every other problem, where we're going to have a picture. So I'm going to start with my beautiful river right here. I'm going to put an arrow in the river, and my V of river, according to this, is 1.20 meters per second. So the velocity of the river, hold on, let me try to get this focused a little better. It's the struggle we all lead. Don't autofocus, that's the problem. Well, still kind of fuzzy, but it's the best we got. Okay, so we've got our velocity of the river. And then we're going to do, we'll do purple for the boat. So then I've got my boat, and it's down here. And the boat is going to be attempting to cross, and then our velocity of our boat is equal to 1.85 meters per second. Okay, and we're going to go down this list. We're going to figure out all of these pieces of information that it has given us. So first question, what is the velocity of the boat relative to someone on the shore? Well, someone on the shore is going to see that the boat is moving upwards a certain amount, or it's moving across at a certain speed, and it's also going to be getting carried by the river a certain speed. So if we wanted to describe the actual velocity of someone relative on the shore, we would want this vector right here. So this would be the velocity of someone who saw this on the shore. It would be this green arrow that wouldn't actually be curved right here. Well, I mean, this is just a right triangle. This is a right angle right there. So we can just use our Pythagorean theorem for this. We can just use a squared plus b squared equals c squared. And then we'll need to solve for an angle to describe it. So we can solve for that angle with our tangent of theta equals opposite over adjacent. So just like we kind of did in the earlier problem, we can actually solve for these two pieces of information pretty straightforward. So we're going to go ahead and do that. So our velocity of the shore, or relative to the shore, is going to be equal to square root of our 1.20 squared plus our 1.85 squared. So we're just going to plug that into our handy dandy calculator. Square root 1.2 squared plus 1.85 squared. You get, according to my calculator, 2.205. So make sure I got the right color there. So I've got 2.205107707. 3 sig figs is the notion in our question. So our velocity relative to the shore is 2.21 meters per second. Now we need to describe the angle for this. So to find our theta, we're going to rearrange this one. So our theta is equal to the inverse tangent So again, all we've done here is we've divided by tangent to move to the other side, so it's an inverse tangent. And then of our opposite of our angle, we're going to use to describe it. And you could use this angle instead, but this is the most logical angle to use, at least I think so. So we're going to do 1.20, and then over our adjacent angle, or our adjacent line, which is 1.85. We'll plug that into our calculators. So we've got inverse tangent. I just had a panic attack because I thought I wasn't recording. 1.2 over 1.85. And we get an angle of, we're going to go to 3 sig figs, so 33.0 degrees. And then we would describe this line as it is going west of north. So west of lightning bolt. No, west of north, not of lightning bolt. So 33.0 degrees west of north, because this is the velocity they would have been traveling. So even though the boat was attempting to sail directly across, the stream will be pushing them down, and so they'll actually travel like this. They'll be traveling in kind of a sloped pattern. So this whole piece right here is our answer to our question. 2.21 meters per second at, we can ignore that top part. This piece right here is the answer to part A of our question, the velocity of the boat relative to someone on the shore. Okay, now we've got letter B. I almost said number B. Letter B. If the distance to cross, and we're actually going to use, because it's going to be relevant now and because we're traveling across and down, I'm actually going to use y on this one. So if our y distance, if our vertical distance to go across is 110 meters, so that implies we're starting at 0 meters, how long does it take to cross? What is the time to take it across? Now, the biggest mistake that people will make in this case is, given the information, yes, they're traveling at this velocity, but we're only concerned with what's going to happen across. We're only concerned with this y direction information, with the going across the river. This velocity is not going to affect it at all. It's not. It's not doing anything for this problem. So if all we care about is the time, we can kind of ignore this. We know this distance here, and so we can just use this velocity. Our velocity in this case is going to be equal to 1.85 meters per second. And then there's acceleration of nothing. There is no acceleration in this example. So if we look at our questions that we've got here, technically we have all the information for v equals v naught plus at, but that's probably not going to do it for us. Really, all we're looking for is velocity equals change in distance over time. So we're going to do v equals delta x over delta t. So our rearranging this, we get time that it takes is equal to velocity over, delta x. Look at that save. Look at that. That was so smooth. Over v. Our delta x is 110 meters. And then our velocity is 1.85 meters per second. A second on bottom of the bottom will take it to the top, so will give us a unit of time. So we've got 110 divided by 1.85. We get a time of 59.4594, whatever. We're going to 3 sig figs, though. So we're going to do 59.5 seconds to cross. So there's our answer to B. It's going to take about a minute, like just a hair under a minute, to be able to travel actually across the stream. Now question C says, well, how far downstream will they move? The key here, and this is going to be the key to a lot of problems this chapter, is that these two things are happening simultaneously. So even though we got to ignore this just to figure out how it's going to go across, remember, it's going to be moving at a diagonal angle. It's going to be traveling at an angle down the stream. So we figured out how much time it takes to go across. That's going to be the same amount of time that it's spent traveling down. We've basically split this into its two components, and we're using each component for two separate equations, but they are linked together by time. They're both occurring in the same amount of time. So now we can say if our initial distance for x this time, because we're going horizontally, is 0, our final x is what we're looking for. Our velocity, in this case, because it's going to the left, we're going to call it negative 1.20 meters per second. Acceleration is equal to 0. We don't have an acceleration, but our t is equal to 59.5 seconds. Now we can do the same equation. We can do v equals delta x over delta t, but we're going to solve for x this time. So to solve for x, we're going to have to go our x is equal to v delta t. So it's going to be equal to negative 1.20 meters per second times our time, 59.5 seconds. Seconds on top, seconds on bottom will cancel out. We'll be left with, and I'm going to carry over this number. I'm not going to use 59.5. So times negative 1.20, I get negative 71.3513, or negative 71.4 meters. So in trying to travel across, if you point your boat directly straight across the stream like they're doing here, you will actually end up 71 meters downriver. This arrow here will actually take you 71 meters this direction to do that. And maybe that's not what you want to do. Maybe you do want to actually go straight across. And if you do want to go straight across, we're going to need to do something in the case of D. And the question on D asks, what angle would you have to position your boat? And I'm going to try to move this camera so I can have the bottom part of my page available. So we're going to redraw our picture here, and we're going to change it a little bit though. So our river is still the same. It's still going to be 1.2. Technically 1.20, but I'm saving some space. But now we're instead going to point this velocity. We're going to point it here. We're going to point it this direction. And we want to know what angle do we need to shoot this at? Or do we need to launch our boat from? To try to end up to go in a straight line, to end up going straight across. So now what we're going to do is we're going to take this information and we're going to draw a new triangle. So what we want is we want our 1.85 to go this direction, and we want that to be our hypotenuse. That's our goal now. And then we're going to have our river be one of the legs of our right triangle. And then we're going to have our velocity be the other leg of our right triangle. So when they combine together, they're going to give us this. So the big mistake is you might think, well, it's just going to be this 33. We solved up here that the angle that it makes is going to be 33. But now we're switching it, and we're going to try to make our speed be the right triangle, or be the hypotenuse. It's going to be the angle, the biggest angle of our triangle. So what we need to do now is plug them in. Let me get my 1.20 here. We want to solve for this theta. We want to solve for that angle right there. So we've got the opposite and we've got the hypotenuse. Opposite and hypotenuse is so. Sine is opposite over hypotenuse. So we're going to do sine theta equals opposite over hypotenuse. If we rearrange that, we will get theta equals inverse sine of opposite of it is going to be our velocity of the river. So opposite is 1.20. And hypotenuse in this case is now our 1.85. So we're going to plug this bad boy into our calculator. Second sine 1.2 over 1.85. I get that we will have to angle our boat 40.4 degrees. And again, you have to describe the angle. You can't just give an angle. In this case, this is the first piece that's going a cardinal direction. I don't think I've actually explicitly mentioned how I do this in my head. So what I do is I say, okay, I find whichever one is a cardinal direction is going north, south, east, or west. So this one is going to the north. And then I figure out which direction does the angle go if that's the starting point. In this case, if this is the starting point, it's going to the east. So I will call it east of north. So if they actually want to angle it so that we end up at the opposite side of the river, exactly where they launched, if they wanted to shoot it like this, the vectors will combine in such a way if they position their boat at 40, until of course it was off screen, at 40.4 degrees to the east of north. So that is how you do a relative velocity equation. If this makes sense, that's good. That's going to make the next few sections we get to a lot easier because it's going to involve a lot of this trig logic stuff like we're working out here. That didn't make sense, please let me know. I'll be happy to answer any questions. Just shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.